Hello and welcome to Ask Echometer. My name is Carrie Ann Taylor, and along with myself from Echometer today, we have Gustavo Fernandez, who will be presiding over the chat and the Q&A session. Also, Ken Skinner, Dieter Becker, Tony Podio, and Lynn Rowland, who will be presenting today. We want these sessions to be interactive, and we like to see you. We love to hear from you. We welcome your questions and comments, and our goal is to answer all of your questions during the session time. So we have an Echometer webpage that is accessible from our echometer.com website, and you can go there right now and download the Session 23 PDF documentation bundle, where you'll find a copy of today's presentation and also a few technical papers that Lynn will reference today. Right next to that PDF bundle link is a link to download the TAM data sets that Lynn is going to use today. So if you don't already have the TAM 1.7 software installed on your computer, you can download it from the software page, or there's a link directly from the home page that goes directly to that TAM 1.7 install. So today's session is titled Identifying Holes in Tubing on Sucker Rod Lifted Wells. And Lynn, I will turn it over to you now.
Thank you, Carrie Ann. Today this presentation is using an acoustic instrument to find holes in tubing. And we've already talked about this topic a little bit in the past. We did an Ask Echometer, the first one, back in May of this year. And we talked about direction of kick. And the direction of kick is used to identify an echo that's basically the echo from a hole. And so I'm going to reference that and pull a few slides out of that presentation. And then we talked about shooting fluid levels on gas lift wells. And Carrie Ann did that presentation, and it was on using the not only fluid level shots, but a technique called dual shot, where you shoot down the tubing with a gas gun, and you have another gas gun attached to the casing, and that gas gun is listening and doesn't make there's no sound on the other side of the pipe because there's no shot. But if there's a pressure communication to the tubing, then you'll start to pick up echoes on the gun that didn't fire. That's called dual shot, and it's a way to find leaky gas lift valves and check valves and holes in tubing, typically on gas lift wells. And then in July, we did one on gas wells, shooting fluids on gas wells. And you know, when someone first told me that we've had holes in gas wells, I said there's just no way there's holes in tubing because there's no sucker rods, and that was completely wrong. There's corrosion, and there's condensation that occurs inside tubing on gas well when the vapor condenses and runs down the tubing wall. If there's any acid gas in the tubing, then it can absorb into the liquid and start to etch away the tubing wall. So it's not uncommon to have a hole in gas wells, and so that's discussed in this presentation here. Now, there's a couple other presentations that are on acoustics I didn't reference here, but we've probably done maybe 7 or 8 presentations at Ask Echometer that have been directly related to shooting fluid levels and analyzing fluid levels and statics and fluid level tests and all different kinds of things. So there's a pretty good body of work now that's online that you can download and listen to a presentation and see data, and then we'll see the questions that we answered during the presentation. But this presentation today is on holes in sucker rod lifted wells. And the presentation is based on 2 technical papers that we presented at the Southwest Petroleum Short Course. One John Sparks and I wrote, and it was presented in 2014, and that was shooting down the tubing with a gas gun on sucker rod lifted wells. And then Joe Norman and I did one in 2015 on using the wireless pressure transducer to pressure test the tubing. And so both of those are techniques that we'll talk about today on identifying holes in tubing on sucker rod pumped wells. Now, um, the first slide shows a dynometer card, which is kind of weird because we're talking about acoustics, fluid level shots, and rod pumped wells. And the question at the top is, well, has your production rate dropped off? And one of the things that is often sometimes confusing on a rod pumped well is when you run a dynamometer on a well that has a hole in the tubing, almost, not always, but often, almost always, the pump is full of liquid, and you'll see a pump card that is it shows that the pump's full. There's no gas in the pump. It shows the valve's working properly, and you're wondering why is my production dropped off or no production, but my pump is full. Well, the answer is well, the liquid's being pumped up the tubing by a functioning pump without any problem, either anchored or unanchored tubing, and the liquid goes out a hole and falls back down to the well, and you're just circulating liquid from in the tubing, out the tubing, back down the pump, and back up the tubing. And in effect, you're not drawing the well down. A well becomes typically staticked out because there's no production from the reservoir. When there's a hole and no production is being produced, then the well becomes static. There's no annular gas flow. Often, if you shoot a fluid level on a well that has a hole in the tubing for a period of time and you measure the casing pressure buildup, there's no casing pressure buildup because there's no flow. So this is a common pump card shape when you have a well that has a hole in the tubing, and typically the height of the pump card, we call that the fluid load, is less because the pump doesn't have to lift the fluid all the way to the surface. It's less than you would expect based on usually the fluid level shot, because the pump has to lift the fluid from the pump intake pressure up to the hole. So often you have a little skinny pump card, not very much lift going on if the hole's down deep. So this a common pump card shape is a full pump card. So when we talk about shooting a fluid level to find a hole in the tubing, we've been shooting fluid levels for a long time, and the idea of seeing a hole in the tubing requires that there be a gas on both sides of the hole. You can't have liquid on one side and gas on the other. You have to have a hole because when the pressure wave goes down the tubing to the hole, it sees an increase in pressure, increase in the volume of the wellbore because there's a hole there, and it causes an inversion of the acoustic signal and echoes back a upside down kick, an inverted kick. And so when you go to a well that the production is off, or there's no production to surface, and you might think there's a hole, the first step would be to shoot the casing. And the well's probably down. It's probably not producing. It's probably turned off. And the well's probably quiet. And you shoot down the casing, and you should see probably no pressure buildup if there's no production, and it should be quiet. And it should be an easy shot, typically an easy shot. And then after you take a couple shots down the casing, then you will shoot down the tubing. Now the tubing has sucker rods in it, and the area, cross-sectional area of the tubing is much less than the casing annulus. And so you may not have to use as much differential pressure to create the shot because it doesn't require as much energy because there's restricted area compared to the casing annulus. And when you shoot down the casing annulus, you're seeing the echoes from the tubing collars, but when you shoot down the tubing, if there's sucker rods with rod boxes or couplings on the sucker rods, then you have a different length of the spacing, and you have to be cautious about using the average joint length in the tubing and the casing, vice versa, because you'll get confused. And so what we usually recommend is that use the acoustic velocity determined from shooting the casing for the tubing shot, so you don't get your average joint length confused between a 31.7 foot average joint length for the tubing joints versus a 25-foot typical sucker rod average joint length. And so we just say use the casing acoustic velocity when you shoot down the tubing, and that way when you see an upkick, you'll have the same acoustic velocity inside and out, and the upkicks will line up, and you'll be able to identify a hole that's above the liquid level. Now sometimes, not always, the sucker rod tends to have more buckling down deep near the pump, and there's more rod-on tubing wear down near the pump, and often, not always, but often, you may have a hole below the liquid level, and so you don't always see an upkick from the hole. You just see fluid level on the inside and the outside of the tubing that's about the same. And if you turn the well on, you don't really see any increase in the liquid level in the tubing as you pump. So you can reshoot the well if you think the hole's below the liquid level, and let it pump for 30-60 minutes, and the fluid level in the tubing won't come up. The pump will be pumping. You'll see the pump action. You'll see a full pump card, but you'll see that the fluid level is remaining about the same depth in the tubing, even though you're pumping. So that's another indication, a way to identify a hole in the tubing below liquid level. Now this is a picture of Ken at the well, and he's got the gas gun attached to casing annulus, and he's going to shoot a little down the casing. This is a wireless gas gun, and we would usually take a couple of shots to make sure those shots repeat. If this well had a hole in the tubing and it was down because of no production of surface, we'd shoot the casing first, and then we move our gas gun over here to the flow T right here, and it would shoot down the tubing. But you would get no results or poor results if there was liquid in the tubing all the way to the surface. So when there's no production of surface, when we shoot down the tubing, we're expecting that there's a liquid level in the tubing, and the liquid level is not at the surface. And that would be the case if there were a hole in the tubing. When you shoot a fluid level, you want to get accurate results, and we talk about, to determine pressure, we talk about that you need to have stabilized conditions to determine an accurate producing ball pressure. And what does that mean? Well, that means that if the well's pumping, it shouldn't have been down for half a day when you shoot the fluid level, because the fluid level is going to change between the time it was pumping and down for half a day, and it's not going to have an accurate producing ball pressure. So we want the well to be operating in normal conditions when you shoot the fluid level to get an accurate representative producing ball pressure. We want to see a good echo, and so if the echo is poor quality, then we need to maybe increase the pressure in our gas gun, or check and make sure there's not a problem with our cable, or maybe even turn off the well to get a better shot because the well is too noisy. So you need a good kick to see the liquid level, and that sometimes requires additional, not just one shot sometimes works. So always take 2 shots and confirm that they show the same liquid level, and if they don't, then do something to make a better shot. The software, the TAM software, TWM software, by default counts the collar echoes, determine the distance of liquid, determines the average joints per second, determines the acoustic velocity. And so it's important, if you're going to use that method to determine distance, that you enter an average, correct average tubing joint length, because that's then used to calculate distance, liquid, and acoustic velocity. And even the gas gravity is dependent upon the average joint length that you type in, because, again, the acoustic velocity is used to calculate the gas gravity. A deviation survey. If you're going to try to calculate pressure is based on vertical depth. And if the well's not vertical, the tubing's out in the horizontal, or you're trying to calculate pressure out in your horizontal well, then you need a deviation survey so that the pressures are corrected for vertical depth versus measured depth. When you shoot a fluid level, the fluid level is measured along the pipe, measured depth, whereas the pressure is only determined or caused due to vertical gradients, gravity. We need a casing pressure, because we want to calculate the pressure from the surface down the well, and so you need an accurate casing pressure. That means you need to do a 0 offset on your pressure transducer, no pressure on the gas gun, before you connect the gun to the well and fire the shot. So we need a 0 offset. We need a pressure transducer that is calibrated and accurate, and that your 0 offset hasn't changed from day to day or from the last shot. If your 0 offset changes a lot, that can mean a problem with your cable. And we want to measure the pressure buildup, and that gives us a gas flow rate up the casing, and that allows us to calculate the percent liquid or the gradient of the gas in the well, gassy fluid in the well below liquid level. So that's important. And then we need the tubing and casing size to calculate the gas flow rate up the casing or up the tubing, weight per foot. And then we need to know the water gravity, the oil gravity, We calculate the gas gravity from the acoustic velocity, so that's usually, sometimes you can input it if you want, if it's a input value, and use acoustic velocity calculated from the gas gravity. But typically, by default, we're going to calculate the average joint length, acoustic velocity from the collar length, and then come up with a gas gravity based on that to calculate pressure. And this says just take 2 shots because geez, you spend all this time preparing your file, getting to the well, hooking the gun up, and then the shot may take a couple minutes. Why not take another one and make sure it works? It's important to take 2 shots. Confirm your first shot's correct. There's no problems with your shots. Now, this is a little shot in a well that has a hole, and you can see here this is the elapsed time of the shot. And here's the shot's fired, and you see a big explosion of noise, which is a release of pressure in the wellbore onto the microphone. And you can see these little spikes here, and all those little spikes represent tubing collar echoes typically. And the software can count that, and the program counted the collar echoes down to here, and it determines the depth based on the acoustic velocity. And when you explode gas in the well, then any decrease in cross-sectional area is going to echo back a down kick. Any increase in cross-sectional area is going to echo back an up kick, and that's what this is. So that up kick is an increase. If you look in your wellbore schematic, there's nothing here that should increase the wellbore. This kick doesn't belong here. And so when you see an echo on the trace that doesn't belong where it is, then either the wellbore hasn't been properly defined, that there's something here that was made when the well was drilled that makes this upkick, or there is a problem in the well that has created a hole, increase in cross-sectional area that we see as this reflection, as this echo. And so we can use our depth reference line to turn that on in the software and move that depth reference line down to this point and identify that this upkick at this depth, based on the counting collars, then this depth of this upkick is 6.45 seconds, and based on the acoustic velocity, it's a depth of 4,457 feet, and that's where we suspect there's a hole in this well and a hole in the tubing. And there shouldn't be any production of surface if that's a hole in the tubing, because that means there's liquid on the inside of the hole, and there's gas on the inside of the tubing at this depth, and gas on the outside, and we could shoot down the casing and see this upkick. All right, so that's an example of a flip of a shot showing a hole in the tubing. Now, so the direction of kick's a big deal. It's how you see increases in cross-sectional area of the wellbore or reductions of the wellbore cross-sectional area. If you shoot an explosion shot into your pipe, tubing or casing pipe, any reduction in the wellbore cross-section will show up as a down kick. And the things in the wellbore that echo like down kicks are the liner, a liner from that reduces the wellbore from the surface down. You'll see the top of the liner as a decrease in cross-section of the wellbore and a down kick. A tubing anchor, you can see through the tubing anchor because it's not completely closed off, but it will show as a down kick. If you have a paraffin or scale deposit that's in a big clump in the wellbore, then it'll show as a down kick. If it's a coating that's a constant diameter, you won't see it. It has to be a change. You have to see a change. You won't see a paraffin or scale deposit if it's just coated on the wellbore and it doesn't show up as a big glob or a sudden change. Blockages. If you have solids that have fallen in or chemicals that's filled the casing or the liquid level, all those things block off the wellbore and those show a down kick. Now, if there's an increase, which is an up kick, if you have an explosion shot, then that is a hole. Perf, if the perf is above the liquid level, you won't see the perf is below liquid level. Open hole, sliding sleeve that is open, casing or tubing that's parted, and the end of tubing. End of tubing it will be an upkick and look like a hole. So you have to be really cautious when you see an upkick at the end of tubing. That's not a hole down at the end of tubing. So that sometimes is confusing. But yeah, end of tubing is an upkick, and it is a hole, but it's supposed to be there. It's supposed to be in the end of the tubing. Now, when you do a explosion shot, that releases pressure from the gas gun into the wellbore. If you do an implosion shot, that means you shoot pressure from the well into the gas gun, And that's a drop in pressure, so the signal you send down the well is upside down. It's a drop in pressure rather than an increase in pressure. And whenever an echo occurs from a drop in pressure, then it's going to be a upkick from a liquid level. It's going to be inverted. But the software has an option. You have to select the details and identify that the type of shot was either explosion or implosion in the software. And then the software displays an implosion acoustic signal or an explosion acoustic signal so that they appear exactly the same. You can't really tell that the shot was implosion or explosion because the direction of kicks are the same, because the implosion shot, when you identify the type of shot, is flipped over 180 degrees, so that a down kick is still a decrease in cross section, an up kick is still an increase in the cross sectional well bore. And that's just showing the details. If you were to select type of pulse, you could pick either implosion or explosion when you acquire the data. Now, what can you see with the fluid level shot when you're trying to troubleshoot the well? Well, first of all, the well is probably turned off. Rod pump well is probably turned off. There's no production surface. Someone found that the well's not producing. It's going up and down, but it's not producing. So you turn it off. The lease operator or someone that went by the well turns the well off and alerts you that, hey, there's a problem with this well. And you come to the well and you take 2 fluid level shots down the casing and verify that the echoes are the same and determine the casing acoustic velocity. And you're assuming that there's a hole because there's no production surface, or maybe even you see an upkick and you've got gas communication between tubing and casing. And so you're going to now take 2 shots down the tubing, but you're going to use the casing acoustic velocity to determine the distance and not use 25-foot rod length if you have 25-foot rod boxes, because as soon as you change the average joint length to 25, then the casing fluid shots are going to be the wrong depth. So just use, for ease and just not to prevent confusion, use the casing acoustic velocity when you shoot down the tubing and the casing for the acoustic velocity in the tubing shot, so you get the accurate distance to the hole, if there's a hole. Now, the well shut in. The well's quiet. There's almost no noise. Usually these shots down the tubing and casing when the well's shut in are easy and the echoes are clear. And I already kind of said this, just another repeat, says don't change the average joint length. Maybe someday in the future, TAM will have an option where you can put an average joint length for the tubing, an average joint length for the casing, but that's not really a working option right now. It's only one average joint length. That's what we use, and that's the average joint length for the tubing is what's used when you shoot fluid levels. All right. What do you get from shooting a fluid level down the tubing? Well, you can find if there's a hole in the tubing. You can see if the well had too much gas pumped up the tubing and the liquid in the tubing is unloaded. And you can see that you need to adjust your back pressure to have higher back pressure on the tubing to prevent gas going through the pump and blowing the liquid out of the tubing. So this is something that you can see. You shoot down the tubing and you can see that the pressure buildup is occurring. You've got gas flowing with the tubing. If it's greater than 0, the buildup's greater than 0. Based on the pressure buildup, you can see how gassy the fluid is in the tubing, and is your gas separator working properly? Yeah, you can actually see how much gas is flowing through the tubing. If your tubing unloaded and you are trying to decide, do I call the water truck to fill tubing up with water to regain pump action, then you can shoot fluid levels and see if the liquid level is gradually coming up as you pump the well, and you don't need to call the water truck to reload the tubing with liquid. If you have a lot of paraffin being produced in this well, it's usually hard to shoot down the tubing because paraffin globs are blocking the acoustic pressure wave, and you can't really use this technique very well. Now this is a well. This is a well that is in our examples, and this is a well that was mentioned in the paper that John Sparks and I did. This is one of John Sparks' wells that was used in the paper, and The well name is BK554, and this is the fluid level shot on the well when the well's acting normal. And we've talked about this in one of the previous Ask Echometer presentations. And you can see the little collar echoes right there, the equal spaced collars. You can see the tubing anchor echo right there. You can see probably the top perf right there. And the liquid level is right down near the pump, and that's the liquid level right there. So this is a normal operation of the well. And fluid level gas-free is only about a joint and a half above the pump intake. In fact, we'd say this well is probably pumped off. It's about 4,458 feet to the liquid level. And the acoustic velocity is 1181, and that's with gas flowing up the casing. So that's the acoustic velocity when the well is pumping, and there's a mixture of gas being produced flowing up the casing annulus. Now, here's the if you click on this screen where you're looking at the acoustic trace, you can bring up the collars tab. This is even showing the date and time of this fluid level shot. And you can see that we've got the collars lined up from 4, and this is 4 to 6 seconds. The software, TAM software, normally just shows 5 seconds, but I went ahead and pulled it out to show 2-second interval. And this shows I've got 11 collars or 10 tubing joints selected, and that gives me an average joint per second of, for this interval right here, of 18.8 joints per second. And when we count all the collars in the well, we get an average of all the collars of 18.23 joints per second, and that's where the distance to the liquid level comes in when we count all the collars. But this one interval from 4 to 6 seconds is 18.8. So it's a little slightly different when you select different intervals, what the joint count is because of pressure and temperature, and sometimes the gas composition change versus depth, and that will affect the collar count. All right, so we got an acoustic velocity of around average 1181 for this well while it's pumping. And then we come back at another day, and this is 1213 versus this was 1114. So about a month later, we come back to the well, and the well's turned off. It's shut down. There's no production surface. And when John shot the fluid level, he can see that the fluid level is high above the pump. He can't see the tubing anchor. He can't see the perfs. He sees a high fluid level, and I think there's no casing pressure buildup in this case. All right, so now something's changed in the well. He has a high fluid level, and the initial shot, he doesn't see an upkick just by inspecting this trace. And so he's going to take 2 shots, and he's going to move his gas gun over to the tubing and shoot the tubing. And I'm going to blow this up here and just show you something though that's kind of hiding in the noise from the collars. So if we look at this trace in a little more detail, you can kind of see that it looks like there's a different, there might be a little upkick and there might be a little downkick, but the noise from the shot's hiding that echo. And so Echometer the TAM software has a method called the low-pass filter to remove all the noise from the collars if you turn it on, and makes the bigger kicks show up and the tiny narrow kicks go away. The narrow kicks are high-frequency signal, typically from collar echoes. And so when we turn the low-pass filter on, we see, aha, there is an upkick right there close to the surface, about 0.6 seconds from the surface. And that's where the hole is. That's our upkick from the casing shot, and if we just glance at this trace, we typically don't see it. So we have to when we're troubleshooting the well, we may have to spend a little more time looking at an acoustic trace and trying to figure out what it's trying to show us. Now, when you shoot the fluid level, he sent a down kick down the well, and when it saw this hole, the pressure dropped and it sent an upkick back up to the surface, and that upkick went back down and echoed again. Now it's a down kick. Why is it a down kick? Because the hole inverts the signal. So a down kick comes, it's inverted, sent back as an up. Up kick comes down, it's inverted, repeats as a down kick, inverted down. And so if you were to look at these echoes, it would go on forever. It'd be up, down, up, down, up, down, up, down. Eventually they die out. But this shows that by applying the low-pass filter, we're able to see a high upkick near the surface, and that's probably where our hole is in the tubing. So now, if we look at the shot, and this is the acoustic velocity of 973 shot down the casing. Okay, and now if we look at the shot down the tubing, this is the shot down the tubing right here. Okay, and now I'm going to try not to confuse you with these two different joints per second. So when we shot down the casing annulus, the average joint length was 32.15 feet per second. And that determined 973 feet per second acoustic velocity. And that's processing this casing shot with that average joint length. If we were to count the colors here and use that average joint length, we would get the wrong acoustic velocity right here. So that's why we say always use the acoustic velocity 973 from the casing shot to determine depth on the tubing shots. But look, we can see an upkick right here. Right there is our upkick. Okay, so the tubing shot already shows us an upkick. We can see it. And when we overlay the trace, TAM has a feature that we can overlay traces, two shots, the casing shot in blue, and the tubing shot filtered in black. No, let's make sure. The tubing shot in blue, and the casing shot low pass filter in black. We can see right there at that point, both of those shots show an upkick at the same depth. We've identified the distance of the hole. It's 263 feet from the surface to the hole. And so we've confirmed that we have a hole. We can show the upkick on both sides of the tubing. It shows an upkick at the same depth. And we found the hole. So that's an example of shooting down the tubing and finding a hole. Now, this is a very old data set. This is a data set I got probably 18, 19 years ago. Came from a guy named D.W. Walker in Oklahoma. And he called me on the phone and said, hey, I've got a well that's not producing liquid to the surface. And I can see a liquid level down near the pump. And I didn't even think you could shoot down the tubing, so I didn't say anything about shooting down the tubing. I said, well, okay, what's your pump card look like? He said, well, the pump is full of liquid. I said, well, that probably means that you're pumping the liquid up the tubing and it's going out a hole and not coming to the surface. So why don't you shoot a level while it's pumping? And maybe if the hole's above the liquid level, you'll see a down kick. That's the down kick he saw. When the well's pumping, and that will indicate that there's a hole in the tubing, and I'll give you the depth of the hole. He said, okay, cool. And then I said, wait. I said, why don't you then turn the well off and wait a little bit, maybe an hour or so, and shoot it again, and if the liquid stops running out of the hole, it'll turn into an upkick. He said, oh, okay. And so here is the shot when it's pumping with the down kick from liquid squirting out in the casing annulus from inside the tubing. And here's the same shot down the casing, but this is the upkick for the hole that you can now see because there's not liquid squirting out the hole. And so this was a way for us to confirm about 20 years ago. And then sometime between 20 years ago and the present, we realized that, hey, we can shoot down the tubing and see the rod couplings and actually use the troubleshooting technique to shoot down the tubing to troubleshoot rod pumped wells with an acoustic instrument. And that was, I don't know, maybe 15 years ago. Someone sent me some data on a well that he'd shot down the tubing and could see the rod boxes. Now, look, this is the same well, and here's our pump card, and the pump card is full. And so this is a well where the liquid is going up the tubing and squirting out this hole right here and falling back down to the pump and circulating between the liquid level and the pump intake and the hole and maintaining a pump filled with liquid. So here's a pump filled with liquid. And the pump card, based on the fluid level shot, says the pump should be lifting liquid from here to the surface, but the pump is just lifting liquid up to the hole. So the pump card height is based on the lift. What's the net lift to based on the pump discharge pressure? Well, it's not very much. And so in this case, it's only up to the hole at 4,005 feet. So the net lift is 2,500 feet versus 6,500 feet if the liquid level was correct based on lifting the fluid to the surface. So the pump car is not as tall. That's what I'm trying to say. The pump car is not as tall as it would normally be. It would normally be this tall up to FO from the level shot, but it's much shorter. So one of the indications of a hole in the tubing for a rod pump well is the pump card is normally much shorter than it would normally be. Now, this is trying to show that if you had the fluid level at the pump, then the pump card would go all the way up to the maximum red line right there, FO max, because that means that the pump is lifting the fluid all the way to the surface with no help from the well, with zero pump intake pressure. And that's how tall the pump card would be. And the fluid level in the tubing would be all the way to the surface if there weren't a hole. And then it would be at the pump intake, and the pump card should be all the way to FO max. Well, it's not. It's not that tall. It's short. Well, if it was liquid level is where it is, there's some oil in the annulus above the pump, then that means that the pump has to do less work because the liquid here is helping lift the fluid. And now the pump card should only be up FO from the fluid level. That's how tall it should be. Well, it's not. It's less height. So what's actually happening in this well is that the pump is lifting the fluid up the tubing from the pump intake pressure based on the liquid in the annulus up to the split joint at 4,050 feet. And that's why the pump is not very, very tall. The lift is equivalent to this height, and this distance right here is equivalent to this distance right here. So that's the lift that the pump didn't have to provide because it's not lifted any higher than the split joint in the tubing. So this is a good indication. Along with your upkick on your tubing, you should also expect to see from the hole on your acoustic trace a pump card that's not full. That's not as tall as it should be, but it's full liquid. Now here's two other examples of wells, but these wells, dynometer cards were acquired with the horseshoe load cell. Now, why does that matter? Well, over here, with the data that's acquired with the polished wide transducer, the way we determine what the loads are is we set the pump card with the polished wide transducer, the load on the downstroke on the zero load line, because we know that the tubing is filled with liquid, and we know the weight of rods and fluid. But if the tubing isn't full of liquid, from here to here the rods are in air, and they weigh more than you think they would weigh because you assume that this is weight of rods and fluid, but this is actually weight of rods in air. So over here we actually weigh the rod string with a horseshoe load cell, and then we subtract out the weight of rods and fluid, but wait, there's weight of rods in air and weight of rods in fluid probably. And so when you get down to the bottom of the pump card's not on zero because you have extra buoyancy that's not being applied to the rods that's missing. So the rod string actually weighs more than what it would weigh the weight of rods and fluid. And that's this distance from here, weight of rods, actual measured, compared to the weight of rods and fluid is a shift in the pump card above the zero load line. So that's another indication, if you use a horseshoe load cell, that the rods are not in fluid. The rods in the tubing are partially in air or gas, hydrocarbon gas. Same thing here. Look, this well right here has a hole in the tubing, and it's got some full pump card, and it's got a little friction right there probably, and the pump card is shifted above the zero load line by, I say, this average distance between here to here, and that's the distance the rods are heavy by the amount of buoyancy that's not being applied to the weight of rods in the tubing. And so this is a missing buoyancy that's not being applied to the rods because the tubing's not completely full of liquid. It has some gas in it, gas on top and some liquid below the hole, gas above the hole, air above the hole. All right, now John was dealing with quite a few wells that were new, and it wasn't uncommon for him to go to a well that wasn't producing any liquid, the rod pump that was turned off, because the well had poor gas separation, and they were pumping lots of gas up the tubing, and then the tubing gradient would get light, and the tubing liquid would flow off, and then the pressure differential across the pump would equalize, and the suck rod pump wouldn't pump. And so we call that a well that had kicked, or the horizontal had kicked and blown the liquid out of the tubing. And so, they found that there wasn't producing any liquid, and they think that there's a hole. Operator thinks there's a hole. Now, it could have been foreign material that stuck the valve open, but maybe the back pressure valve wasn't high enough to keep the liquid from becoming too light a gradient and flowing off. So that's often, the back pressure is not high enough is often the problem in these brand new gassy wells. So you can restart the pump and load it with water, and it'll just start pumping, because now you have a discharge pressure on top of the pump and intake pressure on the bottom. It'll start pumping, but that takes time and money. So John found that you could actually just start shooting a fluid level down the tubing with it pumping, and watch as the liquid level built up toward the surface, and see that the pump's pumping, and not have to call the truck and waste that money filling the tubing back up with water. So that's a practice that he adopted. And so here is a well, and this is a well that John provided called Cabo Blanco. And you can see here, he acquired the day of the polysolid transducer. If it had been a horseshoe load cell, it had been shifted a little bit above the zero load line, because the tubing is partially filled with gas and partly is full of liquid. And it's got over traveled, probably fiberglass rods, pumping fairly fast. But there's no rod stretch because there's no fluid load. So that's another reason why there's a much longer pump stroke than surface stroke. And so here's the shot down the casing, and here's the shot down the tubing, and the fluid levels are pretty close together. And John's thinking at that point in time that probably there's a hole in the tubing below the liquid level, because liquid level and tubing, liquid level and casing are about the same. And usually, if you have a hole in the tubing, they're usually within 1,000 foot or less. And so this is with only about 300 feet, pretty close. And he sees he's been pumping for 25 minutes, and he's using acoustic velocity for the distance down the tubing shot. And this is where they tagged it to get it to pump. Okay. And then here's the first shot right there, distance to liquid after 25 minutes. And then there's a second shot, and look, the fluid level is getting close to the surface after 147 minutes. And then here's the third shot after about 3 hours, and the fluid level is right at the surface. And so he was able to just watch the fluid level and see that the well's pumping the fluid level up to the surface, and then have to have that expense of calling the water truck out and filling the tubing back up to get it pumping. And once it got to the surface, he'd set his back pressure valve, and off he'd go. Now, this says that it's pumping up about 5.7 strokes per minute, because over this time of 31 minutes, it changed from 1,577 feet to 115 feet. At 8.2 strokes a minute, 2.9 strokes a minute. So you can calculate the approximate rise per stroke in feet per stroke. And so then we calculated this volume between the tubing and the sucker rod, and then we calculated how fast the volume would be filled based on these different pumping speeds. And we look right here, we can see that for a pumping speed of about 8.3, here's 8 point, right here is 8 and 8.5, and he's pumping a pump displacement about around 200, and so the pump's pumping what it should be pumping. So this is all kind of makes good sense. So this is an example where we shot the fluid level, and the fluid level is rising just like we'd expect based on the annular space between the sucker rod and the tubing. And we can see that it's coming up, and the pump's pumping exactly what it should per stroke based on the pump displacement and based on the fluid level shot. And then we left the well pumping with 450 psi back pressure on the tubing, making 286 barrels a day, and that worked out just great. All right, now sometimes the pump could be worn, or there could be a problem with the pump, and if you don't have fluid to surface, you can shoot a fluid level and see if the pump is pumping liquid toward the surface. And some pumps are high slippage pumps, and this is called a pressure actuated plunger. They tend to have fiber rings, or they slip more with more differential pressure. They're usually designed for solids. And so this is an example where John went to a well where the pump card looked like it was pumping, but it wasn't pumping. And so he shot fluid levels down the tubing, and these are a fluid level shot at 148, 157, 212, and 220. And the fluid level hardly changed at all. It maybe only came up like 1 foot per minute, not very much. It came up a little bit. And what's going on? Well, this pump had too much slippage, and so as we pumped in this condition, every amount of stroke into the tubing, the pump displacement would leak right back between the plunger and the barrel. And so this pump was being run at a deep depth, and typically these pumps are run at shallower depths, and there's too much slippage. So it pumped just fine as long as the fluid level was high. It handled the solids just fine as long as the fluid level was high, but once you draw the well down, there's too much differential pressure, and it leaks too much, and it won't pump. And so this is what the pump card looks like. And it should be coming 4.25 feet of liquid in the tubing for every stroke, but it didn't do it. And the reason is because there was too much slippage. And this is just it's not a worn out pump. It's just a pump that's not for the right application. It would be better for a shallow well. It's good for solids, but it's not good for this well because the well's too deep. And so they had to change out the plunger for a more conventional plunger that would have a tighter pump clearance and a lot less slippage. Now, so far we've talked about wells that had no production of surface, and the production dropped off, and then we shot down the tubing because there's no liquid in the tubing down to the hole or down to the liquid level in the tubing. Now we're going to talk a little bit about a pressure test where the production has dropped off, and we're going to use the pressure to sensor, the Echometer pressure transducer, wireless pressure transducer, to check and make sure the tubing holds pressure, and the casing check valve holds pressure, and if there's a back pressure valve, the back pressure valve holds pressure. And the test is done in conjunction with the dynometer test. So as the well is pumping, you're measuring both load and acceleration, and also measuring tubing pressure. You can do this as part of a valve test if you want. And if you see a leaky pump or a leaky troweling valve, then you can also see if the tubing will hold pressure, and is that a pump that's leaking, or is that just a hole in the tubing. So there's different types of tests that you can do here. So a lot of times if you have a problem about a hole in the tubing, you might want to pressure test the tubing. And that's assuming that you're still producing some liquid to the surface. You would just use your suck rod pump to pressure it up. But if there's no fluid to surface, then you would bring a truck, and the well would be shut down, and you would pump clean, treated water in the tubing, and maybe raise the pressure up to maybe 500 psi, and you would monitor the pressure. And if there's a hole in the tubing, it will quickly leak off. And if there's a collar leak, it might leak off slowly. But if the well suck rod pump would produce fluid to the surface, then we could use the suck rod pump to pressure up the tubing, and that's what we're going to talk about next. All right, so here is a well with the polished rod transducer on the well, and the wireless pressure transducer on the flow tee, and the gas gun we shot at fluid level. And we're going to simultaneously acquire the dynometer data and the tubing pressure data for dynometer test, and then we're going to pressure up the tubing with the pump and talk about things that we might see. So here is an example of a pressure test, and you can see that the strokes are 1, 2, 3, and then we stopped, then we closed the valve, and we pumped some here, and then the valve's closed, and then we pumped some more. And well, why is this pressure going up? Well, because in this well there's gas inside the pump, and you pump gas into the tubing, and the gas down the pump is a small volume at high pressure, and as it flows toward the surface, the gas pressure gets lower as it gets closer, it flows to the surface, and then the volume gets bigger, and the pressure, well, not the volume, but the pressure goes up. And so this increase in pressure is due to gas in the pump. We'll see some examples of this. And so right here, we stop the pump, and we pull the brake and stop the pump unit. And then from 1 to 2, we're monitoring pressure at the pressure line, and the valves are holding, and not much is going on. And then this is increasing to gas percolating to the liquid. So this is the gas coming up the tubing, getting closer to the surface, and the surface pressure is increasing, and the pressure goes up as a function of the amount of gas present and the rise velocity of the gas bubbles inside the tubing. That's what's happening right here. Okay, from 3 to 4, we take some strokes, and then we stop. Take some strokes right here, and we stop, and take some more strokes, and we stop. And we've only raised the pressure from about, it looks like about 25 up to about maybe 130 almost. All right. And so this is a plot of the pressure versus time, and we can see that in this well, when we stopped, that the pressure built up and it didn't leak off, and so the tubing is fine. And also, since the pressure increases after we stop, that's an indication of free gas in the pump that's been discharged into the pump at the pump discharge. And as the gas bubbles come to the surface, the pressure gradually increases, and then right there we open the flow T and release the pressure. That's what that says right here. Okay. Now this is a well, and this well is it says pressure test PT is okay, pump is full of liquid, and so that's this example. And we do a pressure test, and the pressure holds, and the pump is filled with liquid, and the calculated pump displacement is what we're getting in the tank. And so the liquid production matches the production rate, and so this well doesn't appear to have a hole in the tubing because we're seeing a good match on our adjusted pump displacement with the liquid in the tank, and there's not a drop in pressure. Now, when the pump is full like this, and there's no gas in the tubing, and you close the flow T at the surface, the pressure quickly builds up in a few strokes. And so one of the things that you have to do is determine how many strokes that you can stroke before you overpressure the well. And so, one person would be at the front, and he closes the flow valve, and another person would have to be at the back when the desired pressure is reached. So it could be a two-person job. But if there's only one person, you can't be at the front and the back at the same time and not know what the pressure is. And it'd be easy to overpressure the stuffing box while he's at the back of the pumpkin deciding when it's time to stop. So what we found is we have to do a short test prior to shutting the well in and determine the number of strokes required to reach the desired pressure, and we call those the pump up strokes. So in this well, it just takes about 3 strokes, since the tubing is full of liquid, and you get about 166 psi per stroke. So this is a valve test, and here's the pressure during the valve test, and you can see here that we're at the well, we close the valve, and there's 1, 2, 3, 4 strokes, and the pressure's at 600. So we know we're not going to let it go more than 4 strokes. We release the pressure, okay, and we're pumping, and then we close the valve, and we walk toward the back of the unit, and we count the strokes. When the strokes gets to number 4, we stop, and we hold the pressure, and then we turn for 1 stroke, and then we wait, and then we check and see the pressure's being held, and we leave the pressure off, and this test shows us that there's no there's no hole in the tubing. So this is an example where the well held tubing pressure and didn't leak off due to a hole, and it's full liquid, and it builds pressure fairly quick. And so that's what we see here. And there's our 3 pump up strokes. Here's when we shut the tubing in on stroke number 8. Here's we pull the brake to stop it. Then we went 1 more stroke and pull the brake again. Then we opened it back up. So that's what that shows. Now, one of the things we saw when we shot a fluid level was when the pump isn't pumping liquid to the surface, it only lifts liquid to the hole, then the pump card is going to be very tall. And so you might suspect that there's a hole in the tubing. We go to the well, and you run a dynometer test, and you see that there's a little short pump card here, but you're not so confident there's a hole because the fluid level's high, and the fluid level, FO from the fluid level, kind of matches up with the pump. And so you think, well, I better run a tubing pressure test here and see if I can raise the pressure. And sure enough, this pump raises the pressure quickly at the surface, and the pressure holds, and it indicates that there's not a hole in the tubing. And so this is a well that has too much the runtime is only 50% and needs more runtime to produce a well and draw the well down. And so here, this is from 0 to 600 psi, and this is elapsed time in seconds. And you can see here how many strokes it took to raise the pressure up to about 500 psi, about 3 strokes. And so here we shut the tubing in, and there's 1, 2, 3 strokes, and we stop it. And we notice that the pressure is now I'm blowing this up here, is gradually dropping from 580 psi down to 530 psi. Is that a leak? Why did the pressure drop? Well, if there's gas in the pump, the pressure goes up. And if there's only liquid, the pressure drops slightly. Why? Why does the pressure drop? Because the temperature of the fluids are cooling off to the Earth's temperature and not the discharge temperature of the pump in the tubing. And so you'll see a gradual drop in pressure over time when the tubing is full liquid, but there's no hole. So over 10 minutes, this well had no hole, and we just need to increase runtime. So that's good. We found a well that has no hole in the tubing, little skinny pump card, just wasn't being pumped properly. Now this is showing various strokes, and strokes 25 to 32, and the pump's full liquid. And this is the tubing. So I'm looking at the analysis plot as we're acquiring data, and the tubing pressure is in red. And we can see here the tubing pressure is around 70 to 130 psi, and this is a plunger velocity. We can see that at the somewhere here we're gonna start to increase the tubing pressure. It's 120. Okay, now it's going. Tubing pressure is going up, and we've closed our flow T valve, and the pressure is gradually increasing. And we're going to see how many strokes it takes to pressure up to like 500 psi. We're doing a number of pump-up strokes, and then once we get to number of pump-up strokes, we're going to release the pressure. Here we release the pressure, and the pressure is dropping back down. So that's just an example of trying to determine how many pump-up strokes we would have to have when the pump is full liquid. Now it's back down to normal. Now, one of the things that we noticed when we do these pressure tests was, what's that? What's that noisy thing right there on the acoustic trace when we first shut the well? And is that a leak? What is that? Well, if I take this right here and I expand this to the full scale, this time from about 9 seconds to 9.5 seconds, and I expand this out, I see that this is a wave. And when I stop the well, when its tubing's full of liquid, then that's creates something in the tubing called a water hammer. And the pressure wave travels down the tubing to the pump and back to the surface, and that's an echo. That's an echo in the tubing, and it can create a fairly big increase in pressure at the surface. And so this repeating echo is about 3.5 seconds apart, and we can see that is based on when we stop it, we create this water hammer, this effect, this pressure wave. And the pump depth is 7,977 feet, and it went down and back. So down the tubing, back the tubing times 2, divided by the time equals the acoustic velocity of the water at 4,254 seconds. So these echoes, these repeating echo pressure waves, are due to a sudden closing of flow at the surface, creating a sudden impact, and that echoes up and down the tubing, which is something that's probably normal. I mean, that's something that will happen when you close the valve. And when the pump's full of liquid, it doesn't happen when the pump's full has gas in the pump. All right, so this is talking about the water hammer, and we just kind of talked through that. I'm going to skip this slide here because we just kind of talked to that as we talked to this right here, and go on to this part. Now, this is a pump card when the pump has some gas in the pump. And so when we let the pump up the tubing pressure, it doesn't go very fast because you have to compress the gas in the tubing. So every stroke, we're having to compress the gas in the tubing. And notice that the pressure increase per stroke is small compared to when the tubing's full of liquid. The pressure increases like 166 psi per stroke. Here, it's maybe 5 psi per stroke, not very much. And so this is because, why? Because of this. Because this is free gas in the pump that then discharges in the tubing. And then when you stop at a certain pressure, 500 psi, notice that the pressure gradually increases. Why? Because as it gradually increases, that means the gas that's down at the pump discharge is floating toward the surface. And as it floats to the surface, the gas slightly expands at lower pressure, increasing the pressure over time. So this is a typical pressure buildup when your pump's not full. You'll see a gradual increase in pressure. All right. Now, this is a description of this next slide. So I'm going to go to the next slide and talk about this. So here is a well where there's no production of surface. And the pump card calculates 266 barrels per day. So the pump is discharging 266 barrels a day in the tubing, but there's no flow at the surface. So we can't pressure up the tubing. But there's something important about this. Why is the pump card load all the way up toward FO max? Well, it can't be all the way up toward FO max if the fluid level's down near the pump, and that's what it's saying. The fluid level's down near the pump, and the pump card height is normal height, no fluid to surface. That means the pump is lifting the fluid all the way up to the tubing, to the surface almost. So this indicates probably a hole in the tubing with no pressure increase when we close the valve, but the hole in the tubing is close to the surface. So it could be the casing check valve. It could be oxygen corrosion at the surface of the tubing near the surface. But this is a high hole. This is a hole near the surface. It's not down deep because the height of the pump card indicates we're lifting fluid all the way to the surface. So when we're looking at the tubing pressure versus time, right here we close the flow T valve and the pressure is 0 and it doesn't change. No change in pressure with a closed flow valve means there's no production of surface. That means that there's a hole. The pump card's full, but there's no increase in pressure. Well, this means that there's likely a hole at the surface. Either it's a check valve at the surface is leaking, back down the casing, or it means that there's a hole in the tubing near the surface. Okay, so how do you check the check valve? Well, this little schematic here shows, here is the flow T coming off the surface. Here's a back pressure valve. Here's a valve that we use to pressure up the tubing. Here's where we hook our wireless pressure transducer. Here's a valve that we can close that can make the pressure increase on this valve, or if this valve were open, on the check valve, on the back pressure valve. So we have three valves that we can open and close, and we can check the tubing, we can check the back pressure valve, and we can also check the check valve to make sure that the liquid coming up the tubing and going isn't going back down the casing through a bad check. Now, bad check valves are a common problem. I've heard that the workover crew could put one in backwards. I've heard that they could take out the check and put a check valve in without a check. And so it's not uncommon to have a check valve that leaks. So it's important that, in fact, I know of one field where they check the check valves and 50% of the check valves leak. That means 50% of the wells that you're pumping have fluid coming up the tubing and going back down the casing. That means it's inefficient. It's costing you extra money because you're having to repump fluid that would normally stay at the surface. It's running back down through a bad check. So here is our wireless pressure transducer. Here's our valve number 1. Here is our back pressure valve. Here is our casing check valve. Here's a little valve to close or open, and here's our valve number 2 that we're going to open and close to check all these different devices here. And so we have valve 1 and valve 2 closed. So valve 2 is closed here, and valve 1 is closed. And we're pumping up the well. And so the pressure is increasing. And right here we stop. Okay, and this data right here is the same as this data. So we're stopped. And the pressure is slightly going up because there's some gas in the pump, pressure is slightly going up. And then we open this valve right here, and the pressure that's here then fills this area and pushes against the check valve. Okay? And so when we open valve number 1, okay, right here, right there, valve 2 is still closed, and the check valve has to hold the pressure in that space. Or right here, when we open valve number 1 and the pressure would leak off, we'd say, oh, our check valve is bad. So this is a good technique to check your casing check valve and verify that it holds pressure. And it's a very common operations problem. So can you pressure up the tubing? Well, if you can pressure up the tubing, you can use a pressure test to find a hole. If you think there's a hole, the pressure data is acquired simultaneously in conjunction with your dynamometer test. It provides an enhanced troubleshooting capability. When the pump is filled with liquid, then it's 1, 2, 3 strokes, and the tubing pressure is like 500 psi. So you have to be cautious about closing the flow T at the surface if the tubing is filled with liquid. It'll quickly pressure up. If a hole is present, then the pressure will quickly leak off, or it may not even build up. So that's an indication of a hole. It's either leaks off quickly or it won't build up. Now, if there's gas in the pump, we saw that, the tubing slowly pressures up, maybe 3 or 4 psi per stroke. And the pressure in the tubing will continue to increase after you stop the pump. That's a Gassy pump. When you do a pressure test, you should have your valves arranged so you can pressure test the tubing and then open the valve and pressure test your check valve and pressure test your back pressure valve and make sure they're all holding like they should be. And so that's an important test to do. You can do the pressure test in your valve test and confirm that they're holding, or after you do a valve test, again, do a pressure test and confirm that they're holding pressure. This last sentence is something that I toss in here because sometimes people talk about when the tubing pressure's up during a stroke. And one of the things I wanted to show, and I showed it a little bit, is that the pressure change in the well is a function of the acoustic velocity of the liquid. So water has acoustic velocity about 4,300 feet per second, in that range. And so if your well's 8,000 foot deep, it takes 2 seconds for the pressure wave from the pump to hit the surface. If your well's 4,000 foot deep, it takes 1 second. And so the way the pressure at the surface responds from pressure increases at the pump are related to the pump depth. So if you are in one field and have a rule of thumb about a certain time, and the pressure at the surface behaves a certain way, it really is depth dependent. You need to be cautious about those kind of rules. Now, if you don't have production at surface, then it's time to shoot a flow level, because then you can shoot a flow level down the casing and down the tubing and look for a hole in the tubing. So we've talked about this already. The well typically will be shut in if there's no production at surface, and you can shoot down the tubing, and ideally you'll see a liquid level in the tubing, and you'll identify if the hole's above the liquid level in the tubing. You'll see an upkick on both the casing shot and the tubing shot, and be able to confirm that you've identified a hole. And that's what we just said here. They'll be at the same depth. Now, another thing that you need to consider is that if you run a dynometer card and you have a hole in the tubing, your pump card should be much less than the FO from the fluid level calculated pump card height, and you compare your pump card height to FO from the fluid level. But be cautious, because if you have an incorrect plunger size, then the FO from the fluid level is calculated based on input data, and you could have an 1.5-inch pump in your well and have a 2-inch pump entered into your software, and the software will calculate a much higher FO from the fluid level than you actually measure, and that might think you have a hole in the tubing because your pump card is not tall enough. But you need to confirm it with fluid level shots and pressure testing your well, and not pull your pump because the pump card height doesn't equal FO from the fluid level because someone typed in an incorrect plunger size. So be cautious about this right here. Now, when you shoot fluid levels down the tubing and the well is pumping, if the pump is functioning properly, then it's going to add a certain number of foot per stroke of liquid into the tubing, and you'll be able to see that change as the pump pumps. If the pump's not pumping, or if there's a hole below liquid level, and you shoot a fluid level, you'll see the fluid level changes stay the same place, or not come up very quickly if you have a pump that's defective, or that there's a hole in the tubing below liquid level. So you can monitor the liquid level in the tubing, and if it's not moving, that's an indication of maybe a hole or maybe a bad pump. This is a comment about back pressure valves, and when you have poor gas separation or gas going up your tubing, and you don't have enough back pressure on your tubing to keep the gas under control and not flow the liquid out of the well, then it's going to cause you operational problems. And you can use your fluid instrument to check that and confirm that the well has blown liquid out of the tubing and you need higher back pressure on your well. So the acoustic instrument can be a way to check and see that, yeah, my well is pumping now. I'm pumping liquid for the tubing. I must have blown the liquid out with too much gas up the tubing. I need higher back pressure. So this is something that you can use as part of checking out your gassy wells. I really have a lot of respect and value for shooting fluid levels for troubleshooting wells. It's a way to monitor well. It's a low-cost method. It's a good troubleshooting tool. It lets you see down the well inside the well bore without doing anything physical in the well bore. And so a long time ago, when I first started using fluid level data, all I really wanted was a pump intake pressure, produce well pressure. But sometime in the past, it's been quite a while, I realized that I can see down there. I can see what's going on. I can see a problem. I can see kicks that aren't supposed to be there. They're there, but they're indicating a problem when they're there. So acoustic instrument is a great tool to do an inexpensive troubleshooting of your well.
So I guess we go for some Q's and A's, right?
Okay, yeah, sure.
Okay, probably you want to go back to the beginning of the presentation, slides 5 and 6. 6 was a popular one on the chat. I received several private chats on that slide.
So slide numbers, this one right here, okay.
Yeah, 5 and 6, yeah, 6 will be fine, but let me ask you a question before going there. And I have a question from Fred asking, if you have a hole in tubing below the fluid level, will you be able to detect in tubing while you're shooting the casing?
We talked about that during the presentation, and usually when you have a hole in the tubing and you're pumping the well, usually the fluid levels, and that's discussed in the paper in more detail, but if you read John's paper, he'll talk about it a little bit more, but basically what we see is that the liquid level and the tubing and casing are about the same, and when you pump the well, the fluid level won't move up in the tubing because it's leaking out the hole. And so you can't see below liquid level. You can only see above the liquid level because the pressure wave won't travel in the tubing below liquid. So you won't see a hole below the liquid level, but you will see that, typically see that the liquid levels are the same height in tubing casing if there's a hole. And with the well on pumping, it won't move up the tubing as it pumps. So those are two indications of potentially of a hole. Go ahead.
Okay. Regarding slide number 6, that fluid level shot where you have the kick, I have a couple of questions. One from John's asking, to identify the kick, I assume you look for the narrow spikes, correct?
Yeah, that's a good comment.
Yeah, and also
so let me just show you. See how narrow this kick is? If we go look at this well, let me find it. It's farther. This one right here. See, this kick is wide. Okay, it's wider than the other kick. And so this was a split joint. This was a long, let's say, big hole. So the bigger the obstruction, the wider the kick. The smaller the obstruction, the narrower the kick. So if you have a little tiny hole, it's going to be a narrow kick usually. If you have a big long hole, it's going to be a wide kick. So the width of the kick typically is related to the size of the hole. So the bigger the kick, the wider the kick, not the taller the kick, but the wider the kick, the wider the kick, the bigger, longer the hole is. Okay.
Okay. The next question related to that shot as well is, what about other kicks, high kicks above 3 millivolts, pre and post at 6.45 seconds?
See how the trace right here is just kind of going along like that, and then it suddenly abnormally kicks up. It's like this right here doesn't belong with this. I mean, this is just kind of waving along, and it's kind of going up and down, and these are kind of going up and down, and usually, not always, but usually, the hole from something this is probably the noise in the well creating this kind of wave, and then if it was quiet, it would be flatter. So this is probably due to pumping and other things happen in the well, and that's why it's wavy. But often you'll see a general trend of the trace, and all something will just kind of not kind of belong there. It just kind of pops up. So to me, this stands out where these kicks don't really stand out as much. If we were to lower reduce the scaling of the trace, make it smaller, this is still kind of stick out. So normally not always, but normally the hole will stand out with respect to the rest of the acoustic trace.
Yes, and also a couple of more comments on that. So if we look at the background noise, the well's kind of noisy. We have some noise before the shot. And remember, in this presentation, we're not comparing shots on this specific well. What you should do is you should, again, compare the shots, look for that kick repeat, and probably increasing the gas pressure on the gas gun. That may help you to get a bigger kick from that same point. So there are still a few things that you may do to kind of ensure that that kick is actually repeating shot after shot.
Another thing is the low pass filter will help. Often a low pass filter will remove all this noise, these little spiky spikes, and make this more smooth, and then the hole will even stand out even more. So normally when there's a hole, you'll turn the low pass filter on and off to see if it's present.
Okay, thank you. And one more question or comment is on slide number 5, you have named some items or data that we need to have. If we don't have all the data listed in the slide number 5, what is the absolutely necessary to be able to see that there is a hole in the tubing and to determine the approximately depth to the hole?
Well, you don't have to have the oil and water gravities if you're just looking for a hole. You don't have to have the production rate. You don't have to even have if you don't have the tubing casing size, you won't be able to see the gas flow rate, and that may be an indication that you might help you understand what's going on in your well. So you don't have to have the casing tubing size, but I would recommend that. You need the depth. So, that means that you probably need an average joint length, because that's going to give you an accurate depth. If you have a gnome downhole marker, you need that. Something to give you an accurate depth to get an accurate acoustic velocity. Other than that, I think that if you don't have data, my recommendation is shoot the well, even if you don't have all the data. And then later on, when you go back to your office, you can update additional data to the shot, and then reanalyze it. But don't walk away from the well because you don't have the water gravity or the oil gravity. Go ahead and shoot it, and you can update that later on. So shoot it.
Thanks. One more question is, does a hole can affect the color count line? And if a hole matches exactly on a color, can it be visible or concluded when analyzing the all colors window? Kind of two in one here.
Well, see, that's an interesting question. So if we go back and look at this slide right here, see that kick right there? That's the hole. That's a big kick, and the color echoes are tiny compared to this kick right here, and it's off the screen. So, yeah. So we should go look at this example here and answer that question. I'll look at this example, and we can look at this and go onto the color screen and look at that as an example. But the collars are typically small. The echoes from the collars are typically small, and they're noisy. And if you have a large diameter casing, there's more echoes because there's more room, and it's more noisy. And so the low pass filter will take this all away, because the low pass filter is designed for identifying and showing wide kicks. And the low pass filter will make this echo stand out and make these go away. So we'll play with that when we look at the data, okay?
Okay. Now, if you could please go to slide number 37. We have a couple of questions, comments there.
Now this is discussed in the paper, and it was in the original presentation at the short course. Now I like this because it kind of labels what's going on. Go ahead.
No, well, I think one of the questions that I already answered is if the pressure, and I'm sharing the answer, maybe someone else has the confusion, says the pressure increment is not in the pump, but in the tubing, correct?
Right. This is the surface pressure. So this is a pressure with the so here we have this wireless pressure transducer attached at the surface of the well, and this valve is open between the call this a flow T, and so the liquid's being pumped up the tubing and down the flow line. and we're measuring the pressure right there at the top of the tubing. And so this is a pressure that we see right here. And so these events are causing that we close the valve and the gas percolates toward the surface and causes the tubing pressure to go up. And then we take a couple of strokes, and then the pressure keeps going up because gases come close to the surface. So this is the pressure measured at the surface with the pressure transducer, not the pump.
Another person is asking about the depth of the well. Is this a V11 well, correct?
You know, I don't know. I don't think the V11 well produced this much gas, but it could have been. It's been too long. This is 2014. I forgot which well this is, so I don't remember. But it probably is a V11 well because it's handy. It's close to our office.
That would be around 50 to 100 feet, just to answer that specific question.
Right. Yeah, that's right.
For the pump intake, I mean. Well, one more question is regarding the tubing shots. For tubing shots, should it be better with the well stopped?
Yes. I mean, so okay. So that's a good question. So when you come to the well, if there's a hole, you come to the well because the well's turned off because there's no production of surface. So you go there with your acoustic instrument because someone said, hey, there's a problem with this well. I'm not seeing any liquid in the tank. And so normally the well's turned off. And that means that you can shoot down the tubing because the tubing is not full of liquid. Okay, because there's no liquid to the surface. And so you're not, if you attach your gas gun to the tubing and the well's pumping liquid up the surface, then you won't really see anything other than noise because there's no place for the pressure wave to travel. So normally the tubing's going to be, the well is going to be turned off, and you're going to shoot down the tubing with the well turned off. Now, if you're monitoring the well and you're trying to pump liquid up the tubing and monitoring that, I still would shut the well off every time I want to shoot a fluid because there's going to be way too much noise in the tubing if you don't do that. It just, I mean, it'll be noisy. So I would turn the well off temporarily and shoot down the tubing.
Okay. We have one more question before you go to the examples, Lynn. And Jim is asking, how do you avoid overpressure in the stuffing box when increasing the back pressure valve pressure?
That's a different question. You know, you should know your stuffing box pressure rating, and if you're on a well that is likely to flow, then you probably need a stuffing box that can handle excess pressure, because on some of these wells that we are drilling lately, these horizontal wells, there can be a lot of gas in solution even with a pump intake pressure of 500 psi. And so if your pump intake pressure is 500 psi and you got a lot of gas in your tubing, it can flow off if the gas comes out of solution and your tubing pressure is like say 200 psi. So you got a lot of gas coming out of solution from 500 psi to 200 psi, and that's going to cause your well to flow off. So you need a stuffing box that you can likely pressure up and hold pressure on that's higher than the pump intake pressure, so the gas in solution won't come out and cause you problems while you're pumping the well. So I don't know how to exactly answer your question because each stuffing box probably has a certain pressure rating, and you shouldn't exceed that pressure rating. So I don't know other than to say that. And if you're going to if you have gassy wells, then you need to look into purchasing or installing a stuffing box that can withstand high back pressure, or you'll be out there on your well every 2 or 3 days loading the tubing back up with water to try to get the well pumping again.
Yes, most stuffing box packers are rated to 1500 psi, but that's assuming proper ideal conditions and tightening and not wear on the packers, maybe lower than that.
Yeah.
Okay, one more question here, that's related to the dual shot technique. Is the method of connecting two guns in both sides, tubing and casing, then disconnecting the telemetry wire from the tubing side? Is it helpful to confirm kicks holding tubing?
Say that last sentence again, Gustavo. I didn't hear the last sentence.
Yeah, is the method of connecting two guns, both in tubing and casing, and then disconnecting the wire from the tubing side, I mean the microphone cable, is it helpful to confirm holes in tubing?
Yeah, it works the same way. That's a good paper. I didn't reference that paper. If you want that paper, it's on our webpage. It's also the paper on the dual shot is in the package for that. Let me go back to the very front of the. Let me go back to the very beginning. I referenced that paper. And I don't remember which. Okay, so this is acoustic techniques for gas lift wells, and that paper is in the PDF bundle for seminar number 5. So if you want to read more about that process, then you ought to download that PDF package and some of these example datas and maybe watch that presentation. But the dual shot method is a good technique to find where the depth where pressure communicates between the tubing and casing annulus. And so that means there's a hole or a check valve or bad gas lift valve. And so all three of those behave the same. And so if you have a gas gun on one pipe, one side of the tubing and the other side of the tubing, and one side makes noise and the other side doesn't, the side that didn't make any noise to shoot the fluid level is just listening. It won't hear anything unless there's a hole or a pressure leak. So when it hears noise through a hole, through a check, through a bad valve. And then you start to see acoustic signal on the gun that didn't fire. So it's a really good technique. Yeah, so you might want to read that paper. Email us questions if you have questions about that. But the dual shot is a surprisingly good technique for troubleshooting gas lift wells.
Also, in other of the presentations, Kerry has made some mentions about it.
Right, that's this right here. That's the online seminar number 5 that Carrie Ann gave on gas lift wells.
Right. One more question is a good one from Anthony. I said, for these wells that flow off, why do we increase the back pressure and make the pump fight that instead of letting the well do the work for you? Why keeping running the pump if it will unload itself?
Well, that's a good question because you really would like to pump the water up the tubing and let the oil and gas flow up the casing. And so when Anthony was a little baby, they used to set the pump below the perforations and just pump the water up the tubing, and then the well would flow up the casing annulus. But now Anthony likes to drill horizontal wells, and there's no way to set the pump below the perforations in a horizontal well. So the problem is now you can't do that. You can't just pump the liquid up the tubing and let the gas flow and the oil flow up the casing. And so what happens now, yeah, that's right, baby. Okay, I read Anthony's comments. Anyway, my point is that with horizontal wells, we really have a different environment. And when we start to pump gas or gas flows in the tubing, that's okay to get the liquid out. But then when the liquid's gone, there's no differential pressure. There's no pressure on top of the plunger, because now the pressure in the tubing and the pressure in the casing are about the same, and the valves won't work right. They won't close. They don't close. There's no differential pressure, no flow, and so the pump stops pumping. And then for a while, if you don't catch it, the rods are going up and down, pumping, and they burn your stuffing box out. Fluid level comes up, and then the pump starts pumping and fills the tube with liquid, and you have a big leak at the surface because you didn't turn the well off when the tubing unloaded. Now, if you see the tubing unload and turn the well off and don't do anything and wait about a day for the liquid to come up and then start pumping again, you can operate that way, but you'll lose production because the well will not pump. It'll be off for a day. Well, if the level comes up, then your pump up should have stopped. I agree. Your pump up controller should have stopped it, but how long does it stay down? It has to stay down for like maybe 8 hours or longer and someone's saying, "Hey, my well's down," and so then you go out to the well with a truck and you load the truck with water, and you've got people running all over your field with a water truck trying to keep the tubing filled with water so they don't lose production. And so that's what the problem is. The problem is that yes, you could have the well go down and just rest and wait, and the fluid comes up, and then you can start pumping again if the well flowed off. But people typically say we lost production when that occurs.
That
So
is.
All right, Gustavo said I could talk. So
okay,
so
good.
so you talk about running all over chasing water trucks. Instead, right now I've got people running all over chasing back pressure valves. I don't know that. I don't see the value in it that a lot of other people do. And I have begged all of my operations folks, and in 4 years, no one has shown me a well that lost pump action that wasn't just, gas in the top part of the tubing breaking out, but you're still pumping liquid at the pump depth.
We've got a paper that we wrote about 4 years ago that Russell Brown collected data on back pressure valves and gassy wells, and James Harris did it the same kind of thing before, and so we've got quite a bit of data on some wells. And Russell went to a well that had a lot of gas interference, and probably 60%, and it was really gassy, and he let it pump for 2 or 3 or 4 hours until the tubing unloaded, and then it wouldn't pump anymore. And we've got the data on that, so we can look at the data we've talked about in one of the previous presentations, and I think I even show the data. So that data is available, and if you want, email me and I'll send. We can review that data and talk about it, because that data shows that the pump actually stopped pumping and they couldn't get it to pump anymore because the tubing unloaded. And that's what happened. If you pump enough gas up the tubing in a CO2 flood or gassy wells, and you lighten your gradient up, and the well flows off, if you don't stop it, then you're going to cause yourself operational problems. And you're saying Oxy has pump off controllers on all their wells, and we have algorithms in place that recognize that, and we as a practice turn off our wells when they flow off, and we wait for 8 hours or 12 hours before we turn them back on to start pumping, because we've learned that we can operate them that way and not increase our operating costs. That's just one way to do it. I mean, that's a way you could operate your wells and not be adjusting back pressure. Okay, and that would be
that's my thing, is because,
and that may
like
be,
you said, we have pump off controllers on all of our wells.
right. Okay, but that's just a different way to operate, and it's an option, and it may be lower cost than having people adjust back pressure. So when the price of oil is low and the cost to operate the wells are high, then maybe you should consider testing that and evaluating that in a field. But you have to have all the key parts. You have to have pump off controllers, and you have to have the ability to monitor your wells, and then you have to recognize when that occurs, and then you have to leave the well down for a while until the fluid comes up, and you can start pumping it again. Okay.
Yeah.
So that's I mean I just think that's one way you can do it. I don't know if that's a bad way or a good way to do it, but you'll be trading some oil production, I don't know how much, for maybe less running around the field trying to adjust back pressure valves, or even worse, loading water in the tubing and trying to keep it pumping. See, the problem, a lot of people turn Oxy's pump off controllers off when Oxy sell those wells, and they don't have the luxury of having a pump off controller that they can monitor. So that's one of the disadvantages So you have to devote your company to do that. All right. Any other questions, Gustavo?
Not related to this topic. I have a bit of unrelated question here. about the benefits or advantages of detecting paraffin or scale by using fluid level shots.
Yeah, the paraffin is hard to detect because it plugs up the tubing. You can't really see past it. So I'm not sure you can detect the paraffin. Scale, you have to have a discontinuity in the wellbore to see an echo. And if scale is gradual or corrosion is gradual, you just don't see a sudden change. But on the paper we talked about on gas wells, there's a presentation that we do during our 5-day school that talks about identifying corrosion in wells when you shoot fluid levels, because you can see excessive corrosion in collars that is like a hole, but it doesn't communicate. So you can, in some cases, if you're experienced and you have multiple shots in a well over time, compare shots and see changes that could indicate scale or could indicate corrosion. But it's not very easy. It's really hard to do because it takes multiple shots over time or something unique about the acoustic trace that indicates a problem. And it's usually corrosion and scale and paraffin aren't over a small area. They're widespread in the wellbore.
Well, that's all we have so far, Lynn. We still have about 15 minutes for examples.
All right. So I've got TAM opened right here, and if we go into TAM and I go pick a well, and I go to Echometer online, when you install the data, when you click on the example file that we have on the Echometer's webpage, it's going to stick the examples in Echometer Online in a folder called hole, tubing, and then sucker rod. And this is Ask Echometer session number 23. And there's 1, 2, 3, 4, 5 examples on shooting fluid levels down tubing, and 5 examples on pressure testing. And so one of the questions that we had related to this well right here about how does the hole compare to the collar echoes. So I'm gonna open this one up first, and this shot, you can see over here, it's shot down the tubing. Okay, and if you look, you can't hardly see the upkick on the hole. So let me expand this so you can see it in a little bit more detail. So I'm going to pull this, reduce the amount of time displayed, and you can start to see a fairly narrow kick. And if I go into the, and this hole is at about 0.55 seconds, okay, 0.54 seconds on the acoustic trace. So when I click on the collar count method here, it's gonna show 1 second of data, and this upkick is going to be included on the collar count screen. So I click on it, and you're going to see an ugly, terrible screen here. So there's the screen with the collar count, and it's way too scaled up. So I'm going to scale it down, and we're scaling it down a lot. I'm going to scale this one down up here too. Okay, so here's the area that we're looking at from 0 to 1 seconds over this entire acoustic trace, and we're not really seeing it because it just goes straight off the screen. So if I scale this down to make us see just the hole, the collar echoes are going to be tiny. Okay, tiny. Let's scale it down. So here's the point I was trying to make. This is the hole with the high pass filter turned on. If I go here and say raw, then this is what the signal actually looks like. Okay, and that little double kick there a minute ago, that little extra little kick there was created by the filter that makes the collar show up. It's trying to make this be a collar. It's not a collar, it's a kick. So if I go to the raw data, that's what it actually looks like. This is the actual signal, and you can see the collars are tiny, and the hole is not much bigger. But that's an echo. That's the acoustic trace on a high hole near the surface, and these are really hard to see. And so when you go to a well and you suspect there's a hole near the surface, then you have to put a small differential pressure in your gas gun. So see, the well pressure here is like 48.7 psi at the surface. You need to have maybe 50 psi more, maybe 100 psi in your gas gun when you shoot this well, or you're gonna create too much noise from the shot going. See how the shot's off the screen right here? That's because the microphone gets excited by the sun releasing pressure, and it has more amplitude, more height, which is amplitude, compared to the kind of like the baseline. So you don't want to push too hard on the microphone with too much differential pressure, or the whole thing down to 5.5 seconds would be off the screen. And then when you start to scale it down, it compresses these kicks and makes them harder to see. So I guess my point is that if you have a high hull, you can see it. You can see it on the raw data tab, on the raw filter, on the collars tab, and you can see and compare the kick from the hull to the collars. And this is a fairly narrow kick. It's a little hole. And I think that was the question someone asked. Is Gustavo, do you have any other comments that did that answer their question?
I think that should answer the question. Yes.
Okay. Now, the other thing that's nice about this shot is this is the tubing shot, and then there's a casing shot. Let me find the casing shot. This is a casing shot, and you can't really see the hole on the casing shot because again the shot has so much energy in it that the echoes from the collars are hiding the echo from the hole, and the hole is right here, and so you have to turn the low pass filter on to get this kick to show up. Now let's turn this. Let's go back and let's turn the low pass filter back off, and I want to compare this kick right here, this acoustic trace, to the acoustic trace that was shot down the tubing. So if I go to annotations and I say previous shot, the previous shot was at 114, and I click on previous shot, and that brings up this table of data here, and I want to compare the two shots. And so if I go to the one that says 114 and click right here, it's going to overlay these two traces, and I want to be exactly overlaid. And so I'm going to put them together, and now they're both on 0, and you can't see anything here. I mean, because there's too much energy in the shot, and there's too much noise from the collars. And so if I pull in here, it's still pretty hard to see and compare. So when I turn the low pass filter on, okay, then this noise from all these see that it's a lot of noise. So if I apply the low pass filter, now I can start to see that there is the upkick from the low pass filter, and then let me scale this down just a little bit more. There is the kick from the hole, and they're the same place. So one of the features that is really a good feature when you're trying to find holes in tubing is the ability to go into the software and select two shots, the shot you're looking at in black and the other shot here in blue, different time, overlay them, and then you can compare and see, look for a match. And so the match is, yeah, there's an upkick right there. Anyway, I like the overlay feature. I like being able to compare shots with the low pass filter turned on and turned off. This is a good troubleshooting tool. And then you can also use these little dots to zoom in and look at in detail at a particular section of the trace. So I'm looking at a detail section of the trace right here, trying to investigate it, and that's a nice feature in TAM that you can look at not the entire trace, but just a small piece, plus overlay. So that's a good deal. All right, so that's what I wanted to show on this trace. So let's go pick another one. This one, let's see what this one right here was. What was this? I don't remember what this one was for. Oh, I remember now. This was one where it was pumping normally. Okay, let's go back. And so he came to the well and he shot down the well, and the tubing fluid level and the casing fluid were about the same. And this is a well where for likely the holes below the liquid level. And so that's what this one is about. So let's go on to the next one.
Cabo Blanco showed no pump action at the beginning.
Pardon?
The Cabo Blanco is the one that didn't show pump action at the beginning.
Okay, so this one was an ESP in the beginning, and they changed it into a sucker rod. And so when they did the dynometer data on the well, it showed no pump action. Yeah. Okay, so this is the hole in the tubing a long time ago, before I realized that you could shoot down the tubing. And the operator said no production of surface, and the pump card is full. And the pump cards are full, and it's sitting on 0 because the polished rod transistor is used to acquire the data, and all of the pump cards required with the PRT sit on the 0 load line, whether they should or not. And this one should be shifted off 0 by the buoyancy force, and it's not, because the way we zero the pressure, the polished rod transducer, is the 0 offset is setting the pump card on 0. That's how the 0 offset for the load cell is determined. So this pump is just pumping the fluid up to a hole right in here and out, right back out in the tubing and down. And the cool part about this one, this is the one I think is cool, because when you overlay the two shots, and this is the shot that was done after it had been down for 50 minutes. See, look, here it's 148, and then 238. 50 minutes later, he shot the well, and the down kick became an up kick, and that's because when we shot the well, when it was pumping, the pump was pumping liquid up the tubing and out this hole, and that was creating a decrease in cross-sectional area in the casing annulus and a down kick. And then after he shut the well off and waited about an hour, he was able to shoot the fluid level down the casing annulus, not down the tubing, and he saw an upkick. And you can take this. Where did that come from? If you go into annotations, there is a depth reference line you can turn on and slide the depth reference line right there and say, yep, those are the exact same place. That is the whole liquid squirting out in black, and the blue is the liquid has run out of the hole and it's empty, and it shows an up kick. Also, this is a good example where the kick is wider and it's a bigger. This is a split joint. And what DW said was, he said, we dumped a bucket of silver paint down the tubing, and he said, I told him where the hole was, and he said when they pulled the tubing out, it was exactly in the right place, and he was so excited that he could tell him exactly where the hole was, a split joint, by shooting a fluid level. And I thought that was kind of a neat example because of that. So the next one I'm going to show is, how are we doing for time? Okay.
A minute.
This one is the only difference between this one and the one I just showed you. It's a horseshoe load cell, and now the pump card is actually. Let me just show you. Just take a second. So if I go to the dynamometer card and look at the dynamometer card, this pump card, this is calculated. That load line is calculated from the measured loads on the downstroke with the wave equation, subtracting out the weight of rods and fluid from these measured loads, and it should be on 0. Well, it's not, because the assumption that we made was wrong. The rod string is in air down to, and it weighs more, down to the hole. And so when we use, it weighed more, so when we subtract off weight rods and fluid at the pump, it doesn't go to 0, and it would normally. So that's one of that's a big advantage of the horseshoe load cell, is that it actually measures the actual loads, and you can compare those to these reference load lines, and maybe understand a little bit better than using the PRT. But the PRT is so fast and easy, I'd still use it all the time unless I needed to use a horseshoe load cell. What else? This one just shows no. This one just shows no. Let me look. Let's look at another one. All right, this one is a good one to look at, because when we pressure test, this is a full pump, and if we go to the field view and look at it, and we go into annotations and look at the annotations, there's an option here where we can show the pressure test. Show tuning pressure. Okay, so I just turned the tuning pressure on, and now there is a another line on here that you can barely see, that is the tuning pressure. And if we were to show all the events here of all these lines, and we go back to line number 1, there is the tuning pressure. You can't see it. So I'm going to do replay, because replay will show both the, bring replay in here and start replaying it, and it will show the cards in a different color, not black, and the tune pressure in yellow. It's easy to see, and we can see here as we're moving through these strokes how the tune pressure changes during a stroke, and every stroke the pressure just goes up. How much? It goes from, you can see here on this gauge, from about 240, and then it's dropping down to around 100 and something on the downstroke. And so that's just normal. And here I think we probably are starting to increase tuning pressure. Now, if we want to look at it in more detail, let's stop this and close this and stop this and go to the raw data tab and look at all the strokes and look at the pressure versus time. And so on the raw tab, we can select here pressure or whatever, but we don't want to plot position. We're interested in pressure now. And this shows that right here he closed the valve and increased the pressure, and found out that it took 1, 2, 3 strokes to pressure up the tubing. And so then he could say, okay, now I know. Joe Norman said, now I know I can walk to the back of the unit, close the T, walk to the back, and in 3 or 4 strokes I need to shut it, because I'll have my pressure up to about 500 psi. And then when he stopped, it held pressure, didn't leak off. He did another stroke just in the middle. I think that was to check his check valve, and this really probably wasn't a valve test. And then the pressure held, and then he released the pressure. We can use the raw data tab to display the pressure test, and if you right-click on it, you can copy that and place it into a image in a clipboard and put it into a document if you want. So that's available that way. Also on the analysis plots, if you go to the analysis plots, and you can show 2 analysis plots if you want. And this says tuning pressure in red, and then there's pump position in green, or polish rod position in green, polish rod position. And so there is the polish rod position versus pressure. And that's for stroke number 1. You can put a surface load down here, polish rod load versus polish rod position, and that would be the surface dynamometer card. And then you can say, okay, if I run to the peak pressure, the peak pressure occurs right about there, tune pressure, and the polish rod's moved up to about 42 inches. And you can look at the data in terms of whatever you want to plot versus whatever you want to plot. But this is a plot of tuning pressure versus polish rod position, but versus dynamometer card. And if you went to the report and you went and had this show the analysis plot, then on the report in TAM, that could print out. So the analysis plot would allow you to print out whatever you had, however you configured your analysis plot to show there's where the peak pressure occurs at that position on the surface dynamometer card, and it prints out to a PDF. You could email to someone if you're discussing relationship between pressure, position, and dynamometer card loads. So that's where that's another way you get the tubing pressure out. But if you go to the field view, it showed as you move through the card. If we move through the card, you can see how the pressure gauge is changing, and that would be shown in real time as you acquire the data at the well, but also can be shown in replay mode. So I'm just going through and showing you how the tubing pressure is displayed in the software. I guess it's close to time to quit. Is there any other thing you think we should talk about before we quit? All right, Carrie, I guess it's you now.
All right. Well, thank you, Lynn, for a great presentation. Identifying and troubleshooting holes in tubing is always beneficial, especially when we can provide a new method to do that. So thank you. Gustavo, thank you for hosting the Q&A. And we sincerely thank you all for joining us today and for the questions and comments. And Anthony, we appreciate your interaction today. In the event any of you have any follow-up questions, we always welcome your calls and emails, so please reach out to us. So our next session is going to be on December 16th, and it's a special session that we're calling Ask Anything. So please mark your calendars. We'll get the information out to you in the next week or so. And I think it'll be an enjoyable session, and we sure look forward to it. So we appreciate your time today. We're glad you joined us, and we look forward to seeing you again soon. So have a wonderful afternoon. Thank you.
Thank you. See you all next 2 weeks. It's an open session.
December 16th.
Yeah.
So we're going to bring some questions. If they don't have questions to ask, and ask questions.
We'll bring some questions to ask.
Oh, okay.
Maybe we'll give away an Echometer hat. Do we have an Echometer hat?
A virtual one? Yeah, a virtual
A
hat.
virtual one.
All right.
It's not very
Starbucks
encouraging.
gift card. Yeah.
Thank you all.
All right.
Thank you.
Thanks.
Bye-bye. See you in 2
Bye.
weeks.